So this is another video that will help you with your one-dimensional kinematics assignment, but it focuses mainly on free fall. And something you should be aware of is that when something is in free fall, it cannot be touching your hand or a racket, or you can't be in contact with anything. You have to be in mid-air. So as you throw this ball, as you give it its initial velocity, this is not free fall, as long as it's touching your hand. So it has to leave the hand and be here in the air. Now this is free fall. And the instant it leaves your hand, the only force acting on it is the force of gravity. Okay, so the only force is force of gravity. Now, if you're an athlete and you are jumping or running or throwing something, air resistance is really important, and it has a significant effect on those kinds of activities. But for purposes of analysis here, we are going to neglect air resistance. So only force is force of gravity, and we'll have to neglect. It's very, very complicated to calculate air resistance. It depends on the surface area perpendicular to the velocity. It depends on the temperature of the air. It depends on the speed of the object, and it goes up as the speed squared, so it really increases quickly if you're going fast. Okay, so we're going to neglect air resistance. Now, something you have to know absolutely the entire time, because that force of gravity is always pulling it down toward the center of the Earth, that the acceleration is negative 9.8 meters per second squared always. And what I mean by always is whether it's on its way up or it's at the top. So on the way up, at the top of its flight, or on the way down. The acceleration is always, always negative 9.8. Now, you may think that because it's at the top and it stops just for a fraction of a second before it turns around, that it has no acceleration, but it definitely does have acceleration up here because the force of gravity is still pulling on it. If it didn't have any acceleration up here, then it would just stay there forever. It would just stop and not do anything. So clearly it has acceleration. That's why it turns around and comes back down. Okay, so now the velocity is 0 up here. So even though velocity equals 0. So at the top of something's flight, the velocity is 0, but the acceleration is still negative 9.8. And on the way up, negative 9.8. Now let's look at the consequences of that. What does this negative 9.8 meters per second squared do to the velocity of an object? So negative 9.8 is a little bit difficult number. Let's assume it's negative 10. It makes it easier to do these things in our head. So it's a negative 10 meters per second squared. So what happens? You throw something up and give it an initial velocity of 30 meters per second. This will be at t equals 0. The negative 10 meters per second squared means the velocity changes by negative 10, which means you have to subtract 10 meters per second every second. So if it's at 30, subtract 10, and a second later, it's going to be going 20, still up. Okay, so even though the acceleration is negative, it's still moving up. Then you subtract another 10, and so now it's going 10 meters per second at t equals 2. When you subtract another 10, now you're at the top. And this at t equals 3, this is when the velocity equals 0. But like I said, it doesn't stay there. You have to keep subtracting. So now when you subtract 10, it's going to turn around. It's going to have a velocity of negative 10 because 0 minus 10 equals negative 10. And this would be at t equals 3 seconds. The next second, it's going to be negative 20. Just keep subtracting 10. And then the next, oops, I think I counted wrong. 1, 2, 3, this is 4, 5, and 6, negative 30. T equals 6. Okay, so what are some things that you need to say about this? First of all, that notice how at the same height above the ground, whether it's on the way up or the way down, the magnitude of the velocity is the same. So magnitude of velocity, which just means it's speed, is the same at the same heights. On the way up and the way down. Okay, so if you ever know what the velocity is on the way up, you can figure out what it's going to be on the way down. You just have to switch to a negative number. Okay, that's one thing. And the time, also, time to go up equals time to go down. And so if it takes you 3 seconds to rise to your maximum height, well, it's going to take you 3 seconds to fall back to where you started. Now, in real life, that's not true. When you have air resistance, the time to go up is much, much less than the time to go down, because both gravity and air resistance are pulling you down when you're on the way up. But when you're on the way down, air resistance actually slows you down a bit. It's like a parachute. So it takes longer to fall down. Okay, so let's do an example. Let's do an example of like, what is the velocity of a ball that falls from a 3-meter high roof. Just before it hits the ground. Okay, so we want this velocity just before it hits the ground. This is going to be important when we start calculating things like, from what height do you have to fall and land straight-legged that breaks your leg? It's the ground. Okay, now we're going to follow the same rules of one-dimensional kinematics that we did in the last video. We draw a picture. So there's this ball, and it's going to fall down. And the height from which it has fallen is 3 meters. Okay, now we look at the given quantities. Now you may look at that and go, I only have one number, but I'm supposed to be given 3. Well, in fact, you are given 3. So as soon as you see the word fall, you know acceleration is negative 9.8. It's free fall. You're not going to be told it's negative 9.8. You have to know that and put that in yourself. The second thing is that you assume it falls from rest. Now, sometimes the problem will specifically say it falls from rest, but you can assume when something falls, it starts at rest. It doesn't jump down or get thrown down. And so that means its initial velocity is 0. Now, the third quantity, this 3 meters, you have to be careful about using that. The height from which it has fallen is 3 meters, but the displacement of the ball is down. This is negative. And so, and often we use delta y instead of delta x for displacement if you're going up and down, because it's the y direction. You could use delta x in the equations, that's fine, but delta y is more common. So this is displacement. This would be a negative number because it has fallen down. Be real careful there, you have to get that. Fallen down. So even though you're given that the height of the roof is 3 meters, heights are always positive, and that's the roof, has nothing to do with the ball. The fact the ball has moved down means it's negative displacement. Okay, so there's our 3 givens. The unknown is the final velocity. And that would be the velocity just before it hits the ground. Okay, so now we choose our equation that is missing t. And so the equation is vf squared is vi squared plus 2a delta y, or delta x if you like, it doesn't matter. Okay, now we have to rearrange that. It's already rearranged appropriately, but we have to solve for vf. And remember, when you take the square root, you go plus or minus the square root of vi squared plus 2a delta y. And we have to choose which one it is. Pick the negative because ball is traveling down just before it hits the ground. Okay, and so that's why you choose the negative number, because it's got a downward velocity, VF. Okay, you put your numbers in and you get negative 0 plus 2 times negative 9.8 times negative 3. And you notice here that if you don't put that negative 3, you're going to get a negative sign under your square root, and that'll give you an error on your calculator. So this is equal to negative the square root of that positive number, which is 7.67 meters per second. And that's the velocity just before it hits the ground. Okay, so that should do for this video.